Okay.
Still okay? Okay, now,
Yeah.
what we're going to do is analyze the data. And I've put all of these numbers that we measured in the spreadsheet. And so in the first case, the ball diameter was 1.5 centimeters, which we measured. And I calculated the ball mass. You don't have to know how to do this, but it's basically just the volume of the ball times its density. And the density is about 8 grams per cubic centimeter. So that's the mass of the ball. And so when we're asking the question, did the ball fall faster if it's bigger or heavier? This is essentially tells you how heavy it is. It's the mass. And now the next column is the initial height, which we measured with the ruler, and it's in centimeters. And so we started out at 30 centimeters and we went down to 15 and then repositioned it and it got 20 and so forth. So that's the initial height in centimeters. The height of the sensor at the bottom stayed about the same at 5 centimeters. So this is the height change. It's just this number, the initial height in centimeters, minus the height of the clock stop sensor. That's the distance through which the ball fell. So in the first experiment it fell 25 centimeters. Now this distance is along the ramp. This is vertical, but this is along the ramp, so the ramp is sloped. So this distance is 43.5 centimeters to the clock stop sensor. And let's see, so this is, okay, I have to do that. All right, this is the time it took, and we measured that off the timer that I built. This is the average velocity. Well, the average velocity is just the total distance that went along the ramp divided by the time it took to do it. So the average velocity is the distance divided by the time. This is the instantaneous velocity, or basically it's the speed the ball was going at the bottom of the ramp. And I'm not going to prove this, but it is true that in this case, where we're starting the ball from zero and we're uniformly accelerating it in gravitational field or in any other field, the velocity, instantaneous velocity at the end of the travel will be twice the average. So I just doubled this number right here. So we have the ball diameter, we have the mass, and we have the height change, which is very important. We have the distance the ball fell, we have the average velocity, and we have the instantaneous velocity. The time in seconds is what we measured on the timer. So let's go down and compare the experiments we did with different ball sizes. This is the 1.5 or the medium ball, 1.5 centimeter diameter ball. This is the mass of that ball in grams, calculated from density of 7.7 grams per cubic centimeter. This is the 2 centimeter diameter ball, and it's 32 grams. And this is the 1 centimeter ball, which is 4 grams. So you can see that a 2 centimeter ball has 8 times the mass of a 1 centimeter diameter ball. That's because the mass is equal to the volume times the density, and the volume of a 2 centimeter ball is 2 cubed, or 8 times the volume of a 1 centimeter ball. Okay, well anyway, let's compare the results with these 3 different ball sizes. Now these are all dropped from the same distance, 20 centimeters. The height of the clock stop sensor was always 5, and the height change in centimeters always 15. This top experiment's not relevant. We're just looking at the red numbers. The red numbers all came out right around 57. So the average velocities were about the same, 78 centimeters per second, or 0.78 meters per second, with 2 outliers, and those are for the lighter one. And we showed that with a lighter one, under certain circumstances, it sticks. It's stuck to the bolt. So that time is a little bit greater than these times, but we have a way of accounting for that, and to account for it, it's sticking that much. So anyway, it looks to me like we can say pretty definitively that the velocity does not depend on the mass. Okay? Then the last thing we're going to do is we're going to look at all of these different initial heights and our ramp slopes and all that kind of stuff. We changed the slope, did three different slopes, or two different slopes at least. We moved the start position from 43 centimeters to 17 centimeters. We're just going to plot all that data on a graph of the instantaneous velocity at the bottom versus the change in height. And you can see that it falls along the theoretical curve very closely. So that indicates that the rate at the ball falls, or the velocity at the bottom of the travel, does not depend on the angle of the ramp, and it doesn't depend on the mass of the ball, because this is all the data plotted. And some of these are many points on the same point, because we got the same number, as you can see here, say 0.56. It's plotted 8 times at 155. So this point right here is 8 points. So it looks like we agree very well with the theoretical velocity curve. So we can say the large, medium, and the small ball are going very close to the same velocity at the bottom of the ramp. You can say that the theoretical curve is slightly higher than the data, but the fact that it's close suggests that the velocity at the bottom is predicted well by what we said before, which was v equals the square root of 2gh, that equation. And that was in the earlier video. And the fact that it is a little bit lower indicates that we haven't factored in some systematic experimental error, such as the sticking of the ball to the magnet. Now the sticking of the ball to the magnet is going to influence the numbers on the small ball much more than it will on the big ball, because the weight of that big ball overcomes that stiction much more easily than it does on the small ball. So if you go back to this data, the small ball is the one that has the higher times or the lower velocities, the 75 and the 76. And here at the bottom, the one smaller velocity number with the high slope experiment was also the small ball. If you go over to the left here, it's the 1 gram, the 1 centimeter diameter ball, or the 4 gram ball. So back to this, we haven't factored in all the systematic experimental errors, such as the sticking of the ball to the magnet. The other thing is that even theoretically, all the kinetic energy is not accounted for by 1/2 mv squared, because there's a part of that energy is the spinning of the ball as it goes down the ramp. And we haven't factored that in because it's not a very big factor, and I didn't think it was necessary to get that fancy. So anyway, it looks like we verified the theory pretty well, and that's all we've got. So push the red button again.